9.3 is going to be working with geometric sequences and series. We just came off of our study of what sequences and series were and what the notation was for those different types of things that we were asking. Then we looked at a specific type of sequence, which we called arithmetic. We've later recognized that as really those linear types of patterns, those types of equations with a constant rate of change. Now what we're going to do is look at a certain type of pattern that we call geometric and what that entails. So you're going to want to be able to recognize that pattern that we classify as a geometric sequence. And then just like with arithmetic, we were able to come up with a function of n. So a function with respect to n, we also called that a sub n. It was just some sort of input or a position n, and we would be able to define that explicitly. So for the arithmetic, we came up with a sub n is equal to d times n plus c. Here we're going to ask ourselves, what is the explicit equation that will get us any term of any position that we're defining? Then what we'll be able to do is sum up these sequences, either finite sequences or infinite sequences, and what we know of that to be is our series. So let's consider this first one and ask ourselves, is this arithmetic? So to know if it was arithmetic, you would have to ask yourself, is there a common difference from one term to the next? So you would ask yourself, is there some sort of thing that's being added each time to get the next term? In order to answer that, 10 plus what is going to be 20, what we ended up doing really was saying, well, 10 plus x is equal to 20. Well, let's solve for that x, so subtract 20 minus that 10. So that's why we would take one term minus the other to see what is that common difference that's being added each time. So if we did that, we would get 20 minus 10. We would say, okay, yeah, this one's going to have plus 10 being added from one term to the next. Then we're going to ask ourselves what's happening here. Well, when you take your 40 minus the previous, we're going to get plus 20. We can stop right there and say, no, this is not arithmetic. So the difference is not constant, but something is going on here. So I'm going to clear these. What exactly is going on from one term to the next? What you could probably see with this pattern is that we are multiplying by 2 each time. So instead of adding something to get from one term to the next, what we're doing is multiplying by this constant amount each time. What you would notice is if you were to make an XY table, but I'm going to instead do n a sub n, is this very first term was 10 here. The second term was 20, and then the third term was 40, and so on and so forth. But what I want you to see is from here to here, we would have had to take the previous amount times 2, right, to get this 20. Then what we would do is we would take that amount, and then we would also have to multiply by 2 to get this 40. And then we could take this amount times another 2 to get the next, this 80. So what you can see here is we're having this constant multiplication over and over again. You also saw this in one of the puzzles that you came across. Remember this puzzle number 2 that you had to establish the pattern for. What you guys ended up coming up with is a sub n was equal to 5 to the n minus 1. You saw that you would take this black square and it would kind of multiply into cells. So it would multiply itself into 5. And then those 5 would multiply into 5, so you would have another multiplication of this overall times 5. 5 groups of 5, because each black group would multiply into 5. And now you have 5 times 5 here, and all of those would multiply into 5 themselves for a kind of complex type of image over here. So this is the equation that you came across. Now if you looked at this where you looked at this as an area of land and you started out with 81, what we ended up saying was that, hey, you're going to take this and it's going to be 5/9 of what it originally was. Okay, so 5/9 of what it originally was with this whole area. So then what we had to consider is now, hey, these black areas are also now going to divide into 5/9 of what they were. So this amount is going to be 5/9 of what it was. And this would continue on as well. So what we ended up coming up with for this one was 81 5/9 n to the n minus 1 equals a sub n. So what I want you to consider is that this 5/9 is just a fraction. It's like the equivalent of 0.55 repeating, so about 56%. And the idea would be that you're only going to be 56% of what you were before. This thing right here, if we just put a 1 out front, this is like 500%. So this one was definitely growing in size when you considered it and looked at it in that perspective. When you looked at it in the area perspective, it was shrinking in area. So you could see here once again this growth of 500%. I asked you guys on your patterns or on your puzzles, do these graphs look familiar? And they should. What these are exponential growth and decays. This one, of course, is growth by 500%, and this one is decay by about 55% of what it was remaining. So you could see how it's decaying, only being 55% of what it initially was. So this is decay. So here we arrive. Where are we going with this? This is the pattern that we're looking for. A geometric sequence is unlike the arithmetic when there is a constant rate of difference. There's going to be a constant rate of a ratio. So a constant multiplier from one term to the next. So how you come up with that ratio, instead of D, we're looking for R. And what we're just going to be asking ourselves is take 1 divided by the previous to get that ratio. Because overall what we're trying to do here is, if you consider this, is this geometric, and if it is, find R. We're asking ourselves, is there some sort of constant multiplier from one term to the next? And so in order to do and solve for this R, what you could do is set up 1/8 times R equals 1/4. And then in order to solve for that R, we would have to divide by 1/8. Or in other words, multiply by the reciprocal. So I'm just going to do that. And what we would find when we reduced by 4 each, we're going to get 2 and 1. So R is equal to 2. So we just found that if I took 1/8 times 2, I would get 1/4. So same thing here, we're going to just use this, same thing like we did here. I'm going to skip the step of saying I'm solving for the R. I'm going to just ask myself 1/2 divided by 1/4. So in other words, 1/2 times the reciprocal. And what you'll see once again is when you cross reduce, you're going to get 2/1. So here we're multiplying by 2. And then I hope you can see 1/2 times 2 would give us this one. So yes, this is geometric. And R is equal to 2. Alright, so we also need to find that explicit equation or a function with respect to n. So the geometric sequence of an equation is given by this thing right here. This was an awful lot like what we just came off of. It was like the equivalent of saying like 81 times that 5/9 to the n minus 1. Okay, where you have that rate of growth or decay. This one was decay. But you had a rate of change, and then what we're saying is that we're going to bring it up to an exponent because we're multiplying over and over again. And this was the initial amount that we would start with. So one example here is number 28, and what it asks for is write an expression for the nth term of the geometric sequence. So I'm going to actually just go further and say you should find the nth term. So what they give us is this right here. They give us that a sub 1 is equal to 5. They give us that R is equal to 3/2, which is the same thing as 1.5, which is the same thing as 150%. So this is definitely going to be growth. And then we get n equals 8. So what I'm going to go ahead and do is come up with the equation for the nth term. And what you can do is use this. We would have this original start. And then each time we're going to be growing it by this 3/2 ratio. So then it's to the n minus 1. So the idea is I could use this to come across any position that I wanted. If I wanted, for example, just a sub 1, go ahead, plug in 1 for n. Therefore plug in 1 here. And what you would then get is 5 to the 3 halves, or 5 times 3/2 to the 0, and thereby getting the 3 or the a sub 1 that we had from the start. But I actually am going to look for the a sub 8, so in other words the 8th term. So the expression that would signify this would be that expression right there. Whoops, minus. And if you went ahead and plugged that into your calculator, I would go ahead and solve for this and simplify where you can. What you will get is about 85.43. Okay, so there that is. That would be the 8th term in the sequence. 24, they give us a recursive equation. So the recursive equation is a sub 1 is equal to, and then 5. And then remember this, we have a sub k plus 1 equals negative 2 a sub k. So for this one, they want us to determine the common ratio, write the first 5 terms, and then write the sequence as a function of n. So in the end, we're going to want to write like a sub n, but I'm going to write a sub k because that's what they used. So first of all, let's generate the sequence that this recursive pattern is mentioning. And again, this just means to find your next term, we have to multiply negative 2 times the one before it. So if I wanted a sub 2, which is, keep in mind, a sub 1 plus 1, right? A sub 2 is 1 plus 1. We would have to use a sub 1. So that's where I'm going to just take negative 2 times a sub 1, which is my 5 here. I'm going to get negative 10. A sub 3 is going to be a sub 2 times that negative 2. So that's going to be 20. And then a sub 4 is going to use a sub 3 multiplied by that negative 2. We're going to get negative 40. And a sub 5 is going to be 80. So there are my first 5 terms. My ratio, you can go ahead and divide one term divided by the previous, but what you will get every time is that you are multiplying by negative 2. And that should be of no surprise because that's what the recursive pattern defined. So now we need to write this as a function of n, something that would be explicit for us, or a function that I could just plug in for n and get my nth term, or in this case my kth term. So I'm going to write that a sub k is equal to, and I'm going to use this thing right here, my first term, which would be 5, times that ratio, which would be negative 2 to the, and then k minus 1. Note if I plugged a sub 1 in here, I would go ahead and do that, and I would get to the 0, which would successfully get me this first term a sub 1. If I plugged in a sub 2, then I would have 5 times negative 2 to the 2 minus 1, which would be 1, and that would successfully get my a sub 2. I could do this for whatever, like a sub 100, and I could very cleanly and quickly get the value that I wanted for that was in the 100th term. This again would take me a while. Alright, so now that we've covered how to come up with the equation for the sequence, so just a term in a pattern, the nth term, what we also need to be able to do is add these terms or parts of these sequences. This is what we call a series. So when we do that, there's actually something to keep in mind here. There's 2 types of sums or series that we're going to have to tackle for geometric. There's what we call an infinite geometric series and one that we call finite. So when you think infinite, you should think an incredible amount, this unending amount. We're going to end up adding an unending amount of terms. And then we're also going to just take parts of a sequence or little clumps of a sequence, like the first 5 terms or from a sub 2 to a sub 10. We're going to just take these pieces, and then that's what we call finite, and sum them up with a series kind of formula. So let's tackle this first one that's probably boggling your mind. If you wanted to add up an infinite amount so that there was no end, you'll notice here, so I'm summing from I equals 1 to the infinitive term. So the notation here, we don't have any kind of end here, so you're just going to have s is equal to, and then this thing right here is recognizable as infinite. One thing to keep in mind, the only way to do this is if r is less than 1, the absolute value. So keep that in mind, that you cannot do this formula if r is equal to something greater than 1. The absolute value is greater than 1. What we're going to do for this formula is we're going to take the first term all over 1 minus r. But I do have this awkward red flag because if we're not starting with the first term, if we're not wanting to sum up a sub 1 plus a sub 2, we want to do something like a sub 10 plus a sub 11. If this was 11, you're going to have to start with a sub 11 up here. So red flag on that, do whatever you need to star that so that you know. Your book doesn't do such a good job, but you'll be doing a worksheet that has to do with a variety of starting places. So with that said, again, all you're going to be doing is looking at your series. Notice that we don't have an I minus 1 here. That's okay. This is still recognized as geometric because we still have something that's exponential. So again, your first term, whatever you're starting with, you're going to have to calculate what is that first term. And then you're going to have to take that all over 1 minus r. So let's consider this equation right here. I'm going to write this out as 3/10 plus 3/100, just because I think it's easier to look at, plus 3/1000. And what we're trying to do is sum this up. So first of all, let me define what a sub n is here. Is this geometric? Well, if you were to take this second term divided by my first term, what you would get is 1/10. Go ahead and test me if you don't believe me. If you were to take your third term divided by its previous, you would also get 1/10. So we know what's happening here is we are multiplying 1/10 over and over again to get from one term to the next. So I'm going to go ahead and write my very rigid formula. We're going to start out with 3/10. That's my starting place. And then times my rate, which is, we found 1/10, or my ratio, to the n minus 1. So what I am attempting to do with this sequence is sum it up. So I'm going to write that down here. And I'm starting with the first term, a sub 1, okay, all the way up to infinity. So what I can go ahead and do is use that formula that was just defined. So my a sub 1, I would have to plug in, this is my a sub n equation, you would have to plug in 1 here, plug in 1, but what you will find is that we will just get this first term, 0.3. So here's 0.3. All over 1 minus, and then my ratio, which was 1/10. So this is going to be 0.3 all over, and then 9/10, because I will need a common denominator, right? So I would get 9/10, and I am actually going to convert this into 3 over 10 over 9 over 10. And now what I can just do is multiply by the reciprocal here, times 10 over 9, so cross reduce. Cross reduce, what we're going to get is 1/3. This should be of no surprise that, hey, we just added this sequence that has some sort of geometric pattern. We've added it up infinitely. I just said there was no end here. We could go on forever. That's what this indicated. And what we did successfully do is, yeah, that is 0.33333 repeating forever, and that is exactly what 1/3 is. So why are we able to add up an infinite number of terms? Well, if you were to look at a graph like this, what you want to consider is this is decay, right? It's going to be taking 1/10, or in other words, 10% of what this original amount was. So it's going to be decreasing infinitely small, and what we're getting closer and closer to as we get larger numbers out here is 0. We're essentially adding 0 to the end of the line. So if you're adding 0, or essentially 0, it's not going to be changing the total amount at all. It's kind of boggling to the mind, but that's what's happening. This was n minus 1. That's what's happening here. Alright, so that was infinite. Now we're going to deal with finite. So if you are going to have some sort of n, where you do have some sort of end, so you have a sequence that's geometric and you've recognized that pattern and you want to sum up parts of that sequence, then now this is what you're going to be using. So again, we have a sub 1 times a certain ratio to the I minus 1. And then keep in mind then a sub 1, this is also a red flag. If you're starting at something other than 1 here, this is going to have to change accordingly. So do write like a big old star again here. So this is what you are going to have to keep in mind, that we have 1 minus an r. This is self-explanatory. That's just your ratio. N, this is the number of terms that you are adding up. So I didn't go over this clearly in the arithmetic, and I should have, because you also had to use an n, which was the number of terms that you're adding up. And how you find that out would be the top number minus the bottom number, because remember, this was the term that you're going to end at. This is what you started with. So you're going to have to do top minus the bottom and then add 1. And we kind of discussed that at one point. So we'll do more practice with that. So let's look at number 52 here. 52 is, find the sum of this guy. Okay, so if we did want to sum this up, of course you could always plug in and start doing what is a sub 1. And it would be, well, 1. And then you would have a sub 2. And then what's a sub 2? Well, it would be 5 over 2. And then a sub 3, you plug in 3 here to your sequence, because that's what your sequence is. And you would get 5 squared to the 3 minus 1, so 2. And you would get 25/4. And so you would be taking all of these, adding them up all the way up until you got a sub 10. Okay, but again, we don't really want to do that, because that would take a really long time. And we have these formulas that we can use. So what you can do is recognize that this is geometric, totally geometric, and that it's a finite because we have some sort of end. So a sub 1 here is just going to be 1. When you plug in a sub 1, that's what I calculated right here by just plugging 1 in for my n. And then I'm going to have 1 minus, we know that our r is 5 halves. How many terms do we have? Well, it would be a sub 1, which would be 1, 2, 3, all the way up until 10. So you would do 10 minus 1, just like I did over here, which would get us 9. But you actually have to add that plus 1 here to get the true amount of how many terms you have. So you have 10 terms that you're adding. So I'm going to have to take this value up to the 10th, all over 1 minus 5 over 2. Okay, so you will want to type this in on your calculator, but when you do that, you should get 6357. 0.16 is approximately what you will want to get. I'll define what to round to. So you will have to round in this case, and that's what you'll get. Alright, number 60, let's look at number 60 here real quick, and this will be the last one. If we had from n equals 0 to 40, and then here we would have 5 over 3 times 3 to the 5th, or 3 over 5 to the n. So again, this is geometric, it's finite, we're going to want to use this thing. So what you need to be careful is, like I said, we're going to need to do a sub 0, not a sub 1. So you're going to have to calculate what is a sub 0 times 1 minus, we do know my rate, or my ratio, which is 3/5, to the, and then now we got to be careful, because this isn't 40, not like this one where we were able to easily say, oh yeah, if you added up the first 10 terms there would be 10 of them. Since we have an a sub 0 going on that we're starting with, we're going to need to still use that 40 minus 0 and add 1. We actually have 41 terms here. And if you looked at it at a smaller scale, if you were trying to sum up something from n equals 0 to even something like 2, you would need a sub 0 plus a sub 1 plus a sub 2. That's 3 terms right there. So that's why this is always going to work for you. We're going to need then this to the 41st all over, and then 1 minus 3/5. So I'm not going to solve this one out. Oh, a sub 0 then, you are going to have to go ahead and say 5 times 3/5 to the 0, because that's what this function defines. And you just plug in your input value, which would be 0. So this again will be 1, but then this in the end will be 5. So I'm not going to type this in. I'm going to go ahead and let you solve this, but just be very careful. I would solve the top, all of it, and then I would divide it, all of it, by the bottom in parentheses. So make sure you put parentheses where you need, and then multiply that value times 5. So in the future, when you're doing this now, you're really going to have to kind of keep things separate. I forgot to do the finite arithmetic series. So you guys derived this actually, but if you want to define something that's that C D N plus C, and you're doing it from some sort of I equals 1, sorry, my pen's kind of stalling here, to the whatever nth value, you all came up with this, that it would be A sub 1 plus A sub n times n all divided by 2. You all came up with that for reasons that you can define. We'll do some more activities with really defining why these work, but you know why this one works. Now when we're looking at this, really ask yourselves, am I just trying to find a term, just a value in a sequence? Then you're going to be wanting to use these sequence equations. Am I trying to add up a group of numbers of a pattern? Then you're going to be looking at series, and you'll want to ask yourself, am I looking at arithmetic or geometric? If it's geometric, you're going to have two different formulas to consider. You'll want to really tell, is this infinite, going on forever? Is it a dot, dot, dot? Or is it a defined end? Here's your homework. Like I said, the worksheet is going to actually do a lot better to really make you remember that A sub 1 is not always A sub 1 in these series formulas.